Okay, this is Algebra 1, Module 3, Lesson 6, Exponential Growth of the U.S. Population and World Population. So students will compare linear and exponential models of population growth. And we're going to be looking at graphs here. So these are mathematical modeling exercises. Callie and Joe are examining the population data in the graphs below for a history report. Their comments are as follows. Callie says, "It looks like the U.S. population grew the same amount as the world population, but that can't be right, can it?" Joe's response, "Well, I don't think they grew by the same amount, but they sure grew at about the same rate. Look at the slopes." Okay, so let's go to page 2 and answer some questions here. A says, "Is Callie's observation correct? Why or why not?" She said that they grew at about the same rate, or about the same amount, right? Well, if we look at it, we can know that that can't be correct because here in 1950, the world population is at 2,500 million, and the world ended in 2000, or at about 2000, with 6,000 million. Okay, so it grew by about 3,500 million. So the United States, though, only grew about from 150 to about a little over 250, so about 100 million. And what she did not take into account was that these are in thousands. This is in thousands of millions, where this is only in about 50 million, the scale. Okay, she did not take the scaling of the vertical axis into account. Okay, so let's look at this. Yeah, it says no, the world population grew by a far greater amount as shown by the vertical scales. Yeah, because it's growing by thousands of millions, not 50 million. B says, "Is Joe's observation correct? Why or why not?" Well, it does look like the slope is about the same, but once again, when you're talking about growing by 1,000 million and 50 million, it takes in a whole different change. Okay, so that slope is actually, if we had these by the same amounts over here, the world population would be a much steeper than if we had the world's population in the same amount of the U.S. population. If it's only in 50 million, the slope's going to be a great increase here. Okay, so we would say no, Joe did not take into the effect of the scale either. The rate of change, or the slope, is much greater for the population, the world population, than the U.S. population. Okay, it's much greater for the world. Now, let's look at C. It says, use the world population graph to estimate the percent increase. Okay, so what we're going to do is, let's see here, we're starting at 2,500. Okay, so that's going to be the denominators. That's where we're starting at. And we're going to go from 6,000 to about 25. Let's just call it 2,500. Okay, so that's 3,500 over 2,500. And if you do that, that ends up being like 1.4. So that's about a 140% increase. Okay. Let's see here. So using 2,500 million for the years of 1950 and 6,000 million as the year 2000 gives a percentage increase of 140%. And that's obtained by doing exactly what we just did there. Okay. Let's look at D. Now use the U.S. population growth to estimate the percent increase in the U.S. Okay, so we're going to do the same thing. And we start at about 150 million. Okay, so let's just write 150 since we're going to be talking about the same thing in the numerator. And we go to, let's call it 280 minus 150, since that's where we're starting at. So we're at about 130 over 150. And when you do that, that's only 0.87. So that's only about an 87% increase. Okay. And that's exactly what we did there. Okay. So E says, how does the percent increase for the world population compare to that of the world population? Okay. So we're going to look at this. Well, it says, yeah, how does the world population compare to the U.S. population over the same period? Well, how are we going to compare those? Well, we would definitely say since the world is at a 140% increase and the United States is only at an 87%, we would say that the world is increasing much faster. The world population is increasing at a faster average rate than the United States. Yeah, that's what we said. All right, F says, do the graphs above seem to indicate a linear or an exponential population growth? All right, so this is what we've been talking about for the past week or so. Exponential or linear. Linear would look more like an arithmetic formula, whereas an exponential is going to look like a geometric formula or series. Okay. So what we need to look at here is, I think the time frame here that we're looking at, it doesn't matter necessarily about our scaling factors here. I would say that this is probably going to be increasing at a rate of about 70 million a year. I think is what we would calculate the world population at. Because in 10 years, we've increased about 50 million. So it might be about 50 million to 70 million per year. Because if we take into consideration this 50-year span, we've got 3,500 over a 50-year span. So that's about 70. So I think that would probably be a better increase here. Okay, or a better estimate. And the U.S. would probably be, let's look at it over a 50-year period, 150 to 280. So 280 minus 150 would be about 130 over 50. So that's going to be about 2.6. Okay. So when you're looking at it like this, they're growing by about, not 70%, that should actually be about 70 million per year, whereas the United States is only growing at 2.6 million per year. So, and it does look to be linear, right? These are both linear. Okay. For it to be exponential, you would need to see a drastic change somewhere. Okay. So it might be something like this, but then it jumped way up somewhere, or maybe here, and it start increasing greatly. But there's no exponential growth there that looks mostly linear. So that's what we would say. It says in the frame shown, growth would be linear. Yeah. Okay. About 70 million per year and about 2.6 million per year. So what we would say is those would look something like, well, it says, let's look at, get ahead of myself here. G says, write an explicit formula for the sequence that models the world population growth from 1950 to 2000 based on the information in the graph, and assume that the population in millions in 1950 was 2,500, okay, million, or 2,500 million. And in 2000, it was 6,000. So it's what we use. Use T to represent the model, the number of years after 1950. So after 1950. So 1960 would be, T would represent 10, is what that's saying there. Okay. So they want this for, they want this for the world or for the, yeah, world growth. Okay. It says world population there. Okay. So let's scroll back over here to the world. And we've already said that this was an increase of about 70 million per year. Okay. So what we have to do is, since it's going about 70 per year, where do we start at? Well, we started at 2,500. Okay. Plus our 70, well, that looks like times, let's not do that, plus 70 per year. And that's going to be T, 70T, where that represents something after 1950. Okay, so excuse me, 10 years after 1950. Let's see if that gives us something close to our chart. That would be 700. So 25 plus 2,500 plus 700 would get us to 3,200. Okay. In 1960. So that's what we would use. Okay. Okay, they just wrote it backwards. I like putting what we start with first. I like starting with where we're starting at and then go to what we're changing it. So that's the only reason why it's written backwards there. They just wrote it different. So that's not far off. 3,200 and 3,000. When you're talking about millions, is not that big of a deal, I don't think. Okay. So page 3. I think we're going to zero in here on the population growth now of the world. Okay. So we changed it a little bit. How is the graph similar to the world population in that first exercise that we did? And how is it different? Well, it's still measuring world population in millions here, but what's different is our change, or our years have changed. We've gone from, instead of 1950 to 2000, now we're looking at a 300-year span instead of a 50-year span. Okay, so it says this graph uses the same vertical scale, which is what we said, as for the one in the module in exercise 1. The difference is, though, the year from we're looking at 1970 to 2000 instead of 1950 to 2000. And the second thing is that the graph shows that the population growth took an exponential turn in approximately, this says 1850. I would say it took an exponential turn closer to 1900 and even 1950 instead of 1850. There's not that much of an increase between here and here. So I don't know how they would actually have said it was not 1850. I would say closer to 1950. Okay, because that's when we have to see a huge change starting there. Okay, so I think the answer key may be a little wrong on that one. All right. B says, does the behavior of the graph in 1950 to 2000 match that shown on the graph in mathematical modeling exercise 1? Okay. So from 1950 to 2000, what did we say that the change was? We said that it went from about 2,500, okay, to about 6,000. So yeah, it does represent the same thing, right? This is still 2,500 up to about 6 million, and that's all we were looking at. We weren't looking at anything previous. So yes, both graphs show that the 1950s world population was about 20,000. So it's exactly what we said. 2,000, yeah, about 6,000 million and 2,000. Okay. C says, why is the graph from mathematical modeling exercise 1 somewhat misleading? Okay. Well, I would say maybe that the only reason why we could say that it is misleading is because it doesn't give us an accurate representation of the sequences. Okay. And what I mean by that is it showed us that it was a linear growth, whereas it's probably, if we look at it over a longer period of time, it would represent a exponential growth. So the way they say it is the graph of mathematical modeling exercise 1 makes it appear as if the population has grown in a linear fashion, and it's actually probably really grown in exponential if we examine it over a longer period of time, which is exactly what I just said. Okay. D says an exponential formula that can be used to model the world population growth from 1950 through 2000 is as follows. Okay, so this is the actual formula that we're going to look at. F of t when it's equal to 2,519. So instead of 2,500, what we estimated it at, and 1.0177 to t. Okay. So that's the actual growth here for the world. We said like 1.4. We said it was 140. Here they're going to say it's 1.01 because we were only looking at this portion, which is growing exponentially more than where it did from here to here. Okay. So when we're expanded on out there, oh no, this says it is only from 1950 to 2000. Okay, so they've just boiled it down to 1.1 or 0.1 somehow. So let's see what it's talking about here. Yeah, 2,519 represents the world population in the year 1950, which that would be in millions actually. And T represents the number of years after 1950. Use this equation to calculate the world population in 1950, 1980, and 2000. How do your calculations compare with the world population shown on the graph? Okay. Well, in 1950, it tells us it's 2,519. So if we say f of t is equal to, let's redo this, f of t is equal to 2,519 times 1.0177 times 0, right? Anything to the 0 power is 1, so that's going to just equal 2,519. So it should be exactly the same, right, for year 0, because we've not made it any years past 1950 yet. Now, 1980 is going to be about 30 years past our 1950 mark. Okay, so what we would do there is, I'm just going to erase this over here. I'm going to change this to alpha t is going to equal alpha 30 now. We're going to plug 30 in up here. Well, let me bring up a graphing calculator here. That'll be the easiest way for me to show you. Okay. Okay. So we said that that formula was 2519 times 1 point, I don't know why I keep wanting to put a 1.0177, and that would be to the 30th power. Okay, and so now that would be 4,264, and remember that's going to be considered millions. Okay, that is millions. So in 19, oh, we don't have our graph for 1980 here, so we'll actually have to go back. Let's go back and look at our graph for 1980. And yes, okay, that's about 4,264. So that's pretty close, actually. Okay, so that works out real well. Now, if we go in here and talk about our next value, which is 2000, which is going to be 50 years after the 1950 conception there, we're going to have 1.0177 to the 50th, okay, which is 6,056. Okay, let's look at it for 2000 here on the previous. Well, that's pretty close. 6,056 is just above the 6,000 mark, and this seems to be resting just above the 6,000 mark. So yeah, that formula looks really good compared to this graph, the 1950 to 2000 graph. Okay, so, and let me get rid of that. And those were the exact same that we came up with. We came up with 2000, and all we did was change these to 50, where we plugged in that into the calculator, and those are exactly what we got. So alpha 50 was equal to 6,056, and alpha 30 was equal to 4,264. Okay, so they're very similar to our 1950 to 2000